Okay, can you hear me? Good. Okay, well, as stated, I'm Elliot Ogden. I'm a third-year PhD student at the IPR Institute of Physics of Rennes, and I really hope you're not bored with CH3 plus because I'm also working on it. So I'm specifically interested in molecular growth in the interstellar medium due to ion molecule collisions, reactive collisions. A good place to start is, of course, the stellar cycle. So I take a specific interest in cold molecular gas cloud. And the reason for that is in this medium, we have both solid phase chemistry due to the grains and gas phase chemistry due to the local environment. And that's specifically interesting because the grains can be used, have been established to be a catalyst in this medium to produce complex organic molecular molecules. And yet it's specifically interesting to see that most of those molecules are not detected on the grains, but are actually detected once they've been desorbed by a cosmic ray or a UV photon in the radio spectrum via radio telescopes. So one question which suggests is, how does gas phase chemistry impact desorbed comms and hydrocarbons? So first, I would like to talk about hydrocarbons in the interstellar medium. So here on the top left, you can see this astrophysicist periodic table, and here carbon represents around 0.5% of the mass of this medium. That's not much, yet if we decide to take a look at the number of carbon molecules detected up to 2023, it's a bit out of date, we can see that we've detected 132 molecules containing carbon. Now that is very impressive, knowing that we've only detected around 320 molecules. So that's around 40%. That's due to how reactive carbon is, and it makes it a very important molecule to study in this environment. And on the other side, if we have a look at ions, we can see that the ions in the interstellar medium, we've also detected in cold molecular cloud, we've also detected a few. And that's impressive because it's a very weakly ionized medium, but we've still managed to detect 50 of them up to June this year, might be a bit more now. And so I think it's interesting to take a look at ion neutral reactions. The first reason for that is if we take a look at neutral reactions, they not always, but often have an activation barrier, which means some products might not be able to appear through those regular means. Whereas if we take a look at ion neutral reactions, of course, not always, but often, they don't have an activation barrier, which means ion neutral reactions can sometimes be the only route to produce given products. That's one of the reasons. The second one is ion neutral reactions can be a lot faster than neutral reactions, up to 3 orders of magnitudes faster. And I think this is sufficient to say that ion neutral reactions should not be neglected when coming to study the chemistry of this medium. And now that's the part which has been significantly discussed this week. It's the detection of CH3 plus in the Orion bar. This was done by Olivier Bernet et al. And this discovery was done by the James Webb Telescope in the near infrared. And we've already seen quite a few people talk about it, so I'm not going to expand too long on it. But one of the reasons it's very interesting is here, if we take a look at this chemical network, we can see that CH3 plus ion holds a central place in it. And it's important to see how it will play with the different molecules and different atoms in this medium. It also reacts very slowly with H2, which makes it even more interesting. And to study those kind of reaction, we use, it's called the Crésus. That's a picture of it. So it's quite complicated. I'm not going to use this to describe how it works. I'll use a diagram. So first of all, we have this chamber. In it, we have a tank, which will be filled with gas, and a laval nozzle. This will create our neutral axis. And then we're going to want to send ions in it. So we have an ion transmission line, and then we'll sample the gas flow with an ion guide to push those ions to the detection and do our measurements there. So first, I'd like to talk about the Crésus method. So we have this tank, which will be filled with helium or argon or nitrogen. In my case, I use around 100 liters of helium and trace amounts of reactants. So the pressure in this tank is around 300 millibars, and it will be pushed through the laval nozzle because on the other side of it, the pressure is around 0.1 millibar. This will create a supersonic expansion, with an isotropic core, relatively dense, and has a couple of highlights which are very important. First of all, we'll be transforming part of the internal energy of the molecules into kinetic energy, and by doing that, we will lower the temperature around 300 Kelvin, so room temperature, down to 10 Kelvin if we wish to. And this, of course, we'll be thermalizing them at the same moment. And one of the very strong parts of this technique is it's a wall-less chemical reactor, which means all the pollutions we could have due to condensation will be avoided through this manner. And then the next part is choosing a precursor for our ions. So of course, I've tried with different. The first two were acetone and acetonitrile. Unfortunately, we couldn't produce enough CH3 plus ions, so we had to move on to something a bit more toxic, CH3Br, and later on we'll move on to CH3Cl. So here on the top left, you can see an actual picture of the top of the ion source. What's important to note is we have a hollow cathode. This is where we're going to produce a plasma. So it's a soup of different ions, which will then be transmitted to a quadrupole. At this point, we can do a spectrum. So here you can see one here. So that's the current and the mass. It's not a very nice spectrum, but what's important to notice is we are actually producing CH3 plus ions. And once the spectrum is done, we can choose a specific mass 15 in this case, and transmit it to the deflector. So here at the bottom, you can see a CFD simulation of the ions being injected into the supersonic flow. So there's a bit of a trick to it. As you can imagine, the ion come with a certain speed, and we don't want them to go too fast and go through the supersonic jet. And we don't want them to be stopped by the first boundary layers. So it's kind of like pushing a raft into a river. You have to give them enough speed to arrive in the center of the supersonic flow, and then just be pulled by the river to the detector. This simulation, you can see, it's a simulation of the Mach number. The red is where it's going the fastest. The blue is where it's going the slowest. And this is a GIF, so it gives the impression that it's a pulsed system, but it's actually not the case. We're working with continuous flow. So with this method, we can do two types of different, well, we have access to two types of measurements. The first is measuring the kinetic, the rate coefficients of the reactions. To do that, we'll be sampling the supersonic flow at different distances, which will equate to different times of reaction. And then we will change the density of neutral co-reactant we inject, and by doing that, we'll be able to do different curves, and the slope of each curve will correspond to the density times the, a rate coefficient. So then we only have to plot this as a function of the loss rates, and the slope of this curve will be the global rate coefficient of said reaction. So here we've done that for a couple of reactions. So methanium or CH3 plus with ethylene, propene, alene, and methane. I'd like to talk first, so we can see two different tendencies. One for the non-polar molecules, so methane, ethylene, and alene. And we can see that the rate coefficient doesn't evolve much as a function of temperature. This is what we can expect. It's relatively well described by the Langevin model. And basically, it's a description of a charged particle reacting with the induced polar moment, dipolar moment into a neutral particle. But if we take a look at the CH3 plus propene reaction, which has a polar moment, we can see that the reactivity increases rather significantly as the temperature lowers. So this is something which can be described by the Suezhnevich model, which describes the charged particle reaction with a polar particle. So of course, those two models predict an upper limit. They don't actually predict the coefficient rate. So that's the first kind of measurements we can do. The second one is a measurement of the branching ratios. So here we have the little integration point is supposed to be an arrow. So here we're going to work with the CH3 plus methane. So on the bottom left, you can see what was calculated with François Lieg's group. And on the right, you can see a spectrum. So if you look at this spectrum, we can see the CH3 plus ion. Good, that's what we want to work with. And then you can see a little pig here, that's CH2 plus, CH plus here. Technically, there's also C plus here, but it's almost insignificant. And here we can see the main peak, which is C2H5 plus, which is good because that's supposed to be the only product we can see. So that was reassuring. And we can see a couple of other peaks at mass 28 and 27. Those are presumably due to the presence of C2H2 of CH2 plus and CH plus. And we have a couple of other peaks which are linked to pollution. We can talk a bit about that later. So when we were talking about the C3H plus methane reaction, we're quite happy with the results. They work well with what was fine theoretically. But now if we take a look at the reaction with ethylene, C2H4, it's a bit more contrasted, we'll say. So here the idea is we're going to do different measurements at different densities. That's what we see here. And we're going to measure the ratio of each product. So you can see that the slopes aren't constant. So the reason for that is we have secondary reactions which are going to, well, change the branching ratios. But that's not actually interesting for us. So what we want to do is extrapolate from those points a reaction with just CH3 plus and no in brackets no co-reactants. This allows us to find an actual, well, the real branching ratios of the reaction. So here, if we look at the experimental results, we can see that we have about 54%. We have a growth in 54% of cases, and well, no growth in 46% of cases. So that was rather interesting. There is something interesting here in this first calculation, which was, of course, preliminary works. We can see that normally the cyclic C3H3 plus ion shouldn't be produced, yet we do see it here. So this needs to be a little bit of work to do here. But otherwise, we can see that CH3 plus does promote growth at this temperature, and that's important. We'll talk a bit later on why. And then there's this reaction, CH3 plus C3H4. And this one is very interesting because, as far as I know, this measurement wasn't done before. So that's the first. And you can also see that there are a lot more projects there. Unfortunately, well, not unfortunately, but we can also see that this reaction does not seem to promote growth as well as C2H4 did, because here the two channel which allow molecular growth are C4H3 plus and C4H5 plus here, so about 17%. Otherwise, we're keeping around the same mass, or we're even having a lower mass in 50, a bit more than 60% of the cases. So that was interesting. But that's another way of showing those results is, of course, a table. So here, if we look at the CH3 plus methane, we see that it always promotes molecular growth. If we look at CH3 plus ethylene, we see that it promotes growth in almost 60% of the cases, and with propene in only 17% of the cases. Of course, it's way too early to give any tendency to it or not, but it would be interesting to see if this is a trend or if it's just due to those particular reaction. Now I would like to conclude. So if I was to conclude on the CRISM method, it's a unique tool which allows us to do reactions between large neutrals and ions at low temperature without condensation. If we talk about the reactivity of the CH3 plus ion, we can see that it promotes growth at relatively equal rates between, well, room temperature and cold temperatures. And the next step will be the study of CH3 plus with other abundant neutral molecules in the interstellar medium. And maybe, if it's possible, H2 seems to be an interesting co-reactant. And then something else which would be interesting to do is this method could be used to study thermomolecular reaction. And from those reactions, we can derive an upper limit for the associative rates between an ion and a neutral. Now, of course, I would like to well, thank all the people with whom I work, so the research team at the Institut de Physique de Rennes, the engineers, our collaborators, and all of you. Thank you.